Let's record this. Okay, when we talk about machines and use the formulas, whatever is there in this chapter, we are considering something like a lever. Okay, where there are three values. There is a effort at some point, there is a load at some point, and there is a fulcrum at a certain point. Okay, so the distance between effort and the fulcrum is called the effort arm. The distance between fulcrum and load is the load arm. Okay, effort is the force applied at one end. Load is the force applied at the other end. So both are forces. Effort and load are called forces. Now this is very comparable to the first chapter where we saw moment of force. Right? Moment of force is this force into the displacement. And here also force into displacement. It's actually the same thing. Okay, just giving different names. When will this be balanced? When the anti-clockwise moment of force is equal to the clockwise moment of force, right? So that's the same case over here. Okay. So here we have mechanical advantage, which is force. Sorry. What is mechanical advantage? Load upon effort. Now, say you're applying a certain effort, but you're able to lift a heavier load than what effort you're applying. For example, a plier. You're applying a less effort, but the load that is being felt on the other end, the force that is being felt at the load side is getting multiplied. That I'm able to pull out nails from a wall. I can open a nut, which I cannot do with my hand. So what is a plier doing is, it is giving me something called mechanical advantage. It is increasing my force that I'm applying, right? So whenever in this case where the mechanical advantage is, or if the load is more than the effort, then that's called a force multiplier. If I'm able to lift a heavier load with a small effort, then that's called a force multiplier. So in such a machine which acts as a force multiplier, the mechanical advantage will be what? Since numerator is greater than denominator, mechanical advantage is greater than 1. Okay. If I say a machine has mechanical advantage 2 or 3, that means it's a force multiplier. It is multiplying the force. That means in a small effort, I can lift a heavy load. Okay. So keep that in mind. Now, what if it's the opposite? I'm applying a certain effort, but the load is less. The load that is being felt is less. So this machine, what is the point of such a machine? That machine is called speed multiplier. And for a speed multiplier, the mechanical advantage will be less than 1. Okay. Best example you can give is of a gear cycle. Okay. If you put on first gear, it acts as a force multiplier. You can climb mountains on first gear, right? Or a bike or a car. On first gear, the gears are multiplying the force created by the engine. So you're able to climb easily. Okay. Now when you put on the last gear, fifth gear of the car or bike or cycle, then that's a speed multiplier because you can go fast with it. But the force is less. You cannot climb hills with that. Understand? So, yeah. So just keep this in mind. Force multiplier, mechanical advantage will be greater than 1. Speed multiplier, less than 1. What if a machine has a mechanical advantage of 1? Exactly 1. Then it's not a force multiplier, it's not a speed multiplier. Then why do we need such machine? Yeah, mostly it is used to change direction. Change direction means what? Like a pulley that is lifting water from the well. Okay, that pulley is not a force multiplier. It doesn't act as a speed multiplier. It is just changing the direction of application of force. If I did not have that pulley, I'll have to pull the water upwards, which is very difficult. That muscle is not very strong to pull it upwards. But because of that pulley, I'm able to pull downwards. Okay, so that is the use of such a machine where mechanical advantage is 1. There's another machine where mechanical advantage is 1, that is changing application of force. Application of force means, suppose the force has to be applied at a certain point, I'm able to change the point where I'm applying the force. A cycle is another example of that. Okay, how? If there was, suppose the pedal was attached to the back tire. Right? When you're pedaling, which tire is moving, front or back? Which tire are you applying the force on? The back tire. What if the pedal was on the tire, right at the axle of the tire? Then it would be very hard to ride, or you won't have the proper center of gravity and position and all that. So what we're doing is we're putting the pedal in the center of the bike. So that machine acts as this changing application of the force. It's not increasing or decreasing mechanical advantage. This is changing the point of application of force. Okay. So these are three uses of a machine. I mean, four uses of a machine. Either a force multiplier or a speed multiplier, or to change the direction, or to change the application of force. Okay. So mechanical advantage is load upon effort. There's another formula for mechanical advantage, which is effort arm upon load arm. Okay, this distance of the arms. Now, same like mechanical advantage, there is another value called velocity ratio. Velocity ratio and mechanical advantage, mostly they're supposed to be one. Theoretically, they're supposed to be equal. Okay. Velocity ratio formula is distance moved by the effort upon distance moved by the load, or velocity of the effort upon velocity of the load. Okay. So this is a more accurate value of the distance, or distance moved by the machine. For example, a scissors. Okay, the distance moved by the effort is the distance moved by the effort, actual distance, and this is the distance moved by the load, how much the scissor is moving. Okay, so this is a fixed value, it does not change. However old my scissor is, that velocity ratio will not change because it is a physical value, exact distance, exact. But mechanical advantage is the actual effort and load that I'm applying, the force that I'm applying. Now that value will change based on how old my scissor is, how much friction is there between the pivots. You see that the older the scissor get, what happens? I won't be able to cut so well. Okay, if there's too much friction here, I'll have to apply more load and less effort only is being felt on that side. Right. So the mechanical advantage depends on the efficiency of the machine. Efficiency is another word. Efficiency. Okay. If the machine is 100% efficient, then velocity ratio and mechanical advantage would be equal. What did I say? If efficiency is 100%, that means what? Mechanical advantage would be equal to velocity ratio. Okay. But there is no machine which is 100% efficient. A machine that is 100% efficient is an ideal machine. Means that's what everybody wants. It's called an ideal machine. But every machine that we have is an actual machine which has a lesser efficiency. Okay. Less than 100%. Such a machine, the mechanical advantage will be always lesser than the velocity ratio. Velocity ratio will be fixed. If it's 5, it's 5. But mechanical advantage, it won't be 5. It will be 4 or 3, something lesser than velocity ratio. Is that clear? So if you consider all these values, we have a formula for efficiency, which is mechanical advantage upon velocity ratio. And since efficiency is in percentage form, we have to do into 100. Okay, so that's the formula for efficiency. You see, mechanical advantage will always be lesser than velocity ratio. That is why efficiency is less than 100%. If both were equal, then what would be the efficiency? Harish, I'm not getting it. If both were equal, 5 upon 5 into 100, how much is that?
100.
100, no, 5 and 5 will get cut. Into 100 is what? 100, okay? So if both are equal, then efficiency is 100%. But if numerator is less than the denominator, efficiency will be less than 100%. Okay? There's another formula for efficiency, that is work output upon work input into 100. Okay? Work is measured in joules, as we saw in the previous chapter. So work output is how much output we're getting from that machine based on how much input is given. So always the work output will be less than the work input. Say a pump, a motor. Okay, it is taking electricity. That is the work input it is taking. And what output it is giving is pumping the water up. So the work done by the machine, that's the work output, will be lesser than how much electricity it is consuming. The reason is because of losses. There is loss in heat energy, loss in sound energy, right? A motor makes a lot of sound, generates a lot of heat. These are all waste. Okay. So you're not getting the full output because of all those wastes. Okay? A good machine which has more efficiency will not produce heat, no sound. It will just do the work that it is supposed to do. An electric bike compared to a bike which is having petrol and internal combustion engine, which bike will be more efficient? Electric bike, no sound, no heat. I mean, there is heat and all, but comparatively to an internal combustion engine, there is lesser waste. Okay? All right, so these are all the formulas. Okay, six formulas. Mechanical advantages, load upon effort. Mechanical advantages, effort arm upon load arm. Velocity ratio is distance of effort upon distance of load. Second, the last and next formula, velocity of effort upon velocity of load. And then efficiency, mechanical advantage upon velocity ratio into 100, or work output upon work input into 100. Okay, take a minute, just go through this much, write it down, see if there's any doubt from this part of the chapter. Next, you have the three classes of levers, class 1, class 2, and class 3. To remember this, you have to remember FLE. Do you know FLE? Yeah, sure. This is what is in the middle. Okay. So in class 1 lever, fulcrum is in the middle. In class 2, load is in the middle. And in class 3, effort is in the middle. Okay. Whatever is on both sides in whichever order does not matter. Okay. So example of class 1 lever, you can see all these examples. Learn the examples. Okay. Fulcrum is in the center. Now, load could be far away from fulcrum, effort could be close, or it could be the other way. Okay. So depending on what is far away, you have mechanical advantage either greater than one or less than one. See, in this example, if load is far away from the fulcrum and effort is close to the fulcrum, like a scissor, okay, the effort arm is closer to the fulcrum, load is far away. Such a machine is a speed multiplier. Less effort arm. Formula for mechanical advantage is what? Effort arm upon load arm. So if effort arm is small, load arm is big, then mechanical advantage is less than 1. Now, what if effort arm grows big? If effort arm comes to the right, this moves to the right and load closer to the fulcrum. Now, the effort arm is big, load arm is small. So, mechanical advantage will be greater than 1. Okay, so class 1 lever can have both mechanical advantages. Can be a force multiplier as well as speed multiplier. A scissor is a speed multiplier. A plier is a force multiplier because it has a long effort arm. Okay, class 2 lever, load is in the center, fulcrum and effort on both sides. So your load arm is always shorter than the effort arm. Effort arm will always be big. So since effort arm is always big, mechanical advantage will be greater than 1. It's always a speed multiplier. Example of this is like this: nutcracker, bottle opener. So they're all speed multipliers. With sorry, what am I saying? Not speed multiplier. Effort arm is bigger. So mechanical advantage is greater than 1. What type of machine is that? Force multiplier, right? When mechanical advantage is more than 1, it's a force multiplier. So you can multiply the force. The nutcracker multiplies the force that you're applying to crack a nut. Opening bottle. All of these examples, forces multiplied. Okay, and the last example, effort arm is short and load arm is big. So load arm is bigger. That is a speed multiplier. Example, sugar tongs, knife, speed lifting a load. This is the foot pedal of a car. So all of these examples, they are more of convenience. They're not, your aim is not to multiply speed. It is just convenience. For example, sugar tongs or tongs to turn papad while frying. It's similar to this, right? You hold in the center. That's where your effort is. Fulcrum is at the end. and the load, that is a puppet that you're turning, is at that end. Okay, so it has to be in the shape because otherwise your hand has to go inside the oil. So this way, it's more of convenience. That's why we use these speed multipliers, not exactly to multiply the speed. But yeah, it multiplies the speed. If your effort arm, if your the distance of effort is 1 centimeter, the load might move 2 centimeters. It's like this. Your load is, I mean, your effort is moving less, but the load is moving more over there. It's multiplying the speed eventually. Okay, then in your body, how you have all the three types of classes, just memorize that. Your head movement, that is class 1. Lift standing on your toes, that's class 2. And lifting a weight, that is class 3 lever. Yeah. All right, the last topic is about pulleys. In this pulleys, you have to remember what is the velocity ratio for each of these pulleys. A single fixed pulley like this, as we said in the beginning, it has no mechanical advantage. It's no mechanical advantage means mechanical advantage is 1. It's not a force multiplier, it's not a speed multiplier. It is only to change the direction of force applied. Now, when you're drawing any diagram, effort has to be, arrow has to be pointing downwards, load also arrow pointing downwards, tension should be always pointing upwards. And one single rope will have one tension throughout the rope. However, the rope moves around in the system. If it's one single rope, it will have one tension throughout the whole rope. For example, the rope is going like this and all. Okay. At every point like this, you'll draw like this tension upwards. And it's the same tension. Say T1, it's T1 everywhere. Okay. If you have another rope, that rope's tension also is upwards, but that will be written as T2. Okay. All right. So you have a single fixed pulley, then you have a single movable pulley like this. This pulley has a velocity ratio of 2, which means it can lift 2 times the load. Velocity ratio 2 means you can lift 2 times the load. Only thing, the rope has to be pulled twice the distance. To lift something up by 10 meters, you have to pull 20 meters of rope. Okay. Now you use them in combination. One fixed over here to change the direction, and the movable to give it that velocity ratio of 2. Now, instead of using one movable pulley, they use multiple movable pulleys. Okay, so here there are 3 movable pulleys and 1 fixed pulley. So in this system, the velocity ratio will be 2 raised to n, where n is the number of movable pulleys. So here there are 3 movable pulleys. So velocity ratio is 2 is to 3, which is 8, which means you should be able to lift 8 times the load. See how it's multiplying the force by 8 times. But obviously you cannot lift the load. You can't lift 8 times the load because along with the load, you're also lifting these movable pulleys. Their weight also has to be lifted. So mechanical advantage will be lesser than 8, as I said. It's always lesser than velocity ratio. So say it is 6. So what is the efficiency of this machine? Efficiency formula is mechanical advantage divided by velocity ratio into 100. You will see that the mechanical advantage, sorry, the efficiency will be less than 100%. Okay. Maybe, I don't know the calculation, but around 75% or something it will be. It is 75%. Okay, this is 3 upon 4. So that is 75%. Next, we have the block and tackle system. In the block and tackle system, there are 2 blocks, the upper block and the lower block. The upper block is always attached to the top. The lower block is attached to the load. It goes down with the load. And there's only one rope. That rope is called tackle. One rope that goes throughout the whole system. So at every point on the rope, you have to draw the tension pointing upwards. At the right side here, this is where the effort is applied to pull the rope down. And the load is attached to this lower block. Now here the velocity ratio for a block and tackle system, what is it? It's just a number of pulleys. If there are 5 pulleys, velocity ratio is 5. If there are 4 pulleys, velocity ratio is 4. Okay. Remember, the lower block moves along with the load. So if you're lifting the load, you're also lifting the lower block. Okay. So the total weight of the lower block and the load is the actual load that you're lifting. So if you want to lift heavier load, you have to make this lower block as light as possible. The lighter the lower block, the heavier load you can lift. Because you're losing out a lot of lifting load by having heavier pulleys over here. Okay. All right. So I think that is the end of this chapter.
Yes, sir.